Hello, this is Mr. Keppel, and this is PHYZR number 14, Heat Transfer. This is from the Thermodynamics unit, page number 2. The purpose of today's lesson is to discuss the many ways that internal energy can be transferred from one object to another. We'll talk about what causes internal energy to be transferred and the physical mechanisms which allow energy to be transferred. Those mechanisms are conduction, convection, and radiation. We'll be giving some examples of each of these heat transfer mechanisms, as well as a detailed explanation of the way they work. Let's begin with the review. Suppose that a hot cup of coffee is placed on a cold iceberg. What will happen? Well, we know that the coffee is going to cool down. The coffee is going to lose temperature and the iceberg is going to melt a little bit. This is very similar to if you took an ice cube and you placed it into your coffee. So we know that the coffee has a greater temperature than the iceberg. But which object has more internal energy? In other words, which object has more thermal energy contained within it? We know that the molecules in the coffee are moving very rapidly because they have a high temperature. The molecules in the iceberg are moving slowly because they have a cold temperature. So you would think that the coffee has more thermal energy than the iceberg. But that is incorrect because thermal energy or internal energy also depends on mass, and the iceberg has a much greater mass than the coffee. So even though the individual molecules in the coffee have more kinetic energy than each individual molecule in the iceberg has many more molecules, therefore it has more energy within it. It has a greater internal energy. The question I have for you to think about is, in which direction will energy flow? Will the energy from the coffee flow to the iceberg, or will the energy from the iceberg flow to the coffee? Take a moment to think about this. So the question is, does the heat leave the coffee, or does the coldness enter the coffee? This is a question of whether it's heat that flows or coldness that flows. The answer is, it's heat that flows. The coffee is going to lose temperature. It's going to release energy. The iceberg, on the other hand, is going to absorb this energy, and its temperature will increase. So we notice that energy is transferred from the coffee to the iceberg. When the coffee loses energy, its temperature decreases. The molecules have gotten slower. They have less kinetic energy. Whereas in the iceberg, the molecules have gotten slightly faster, so the temperature has increased. There's a gain of energy in the iceberg. We call this transfer of energy heat because it comes from hot places and flows to cold places. So it's not called heat because it's hot. It's called heat because it comes from the hotter object. So what exactly is heat? In physics, heat is represented with the symbol Q, and this comes from the word quantity. So back when thermodynamics was first being discovered, they used to refer to heat as the quantity of heat. And so that kind of stuck with us, and today we still call it Q as the symbol for heat. The unit of heat is the joule, abbreviated with a capital J. And that's because heat is a form of energy transfer. Specifically, heat is internal energy that is transferred between bodies due to a temperature difference. So whenever you have a difference in temperature, there will always be a heat flow between these objects. There will be an exchange of internal energy. One object will release internal energy, the other object will gain it. So we say that heat always flows from hot to cold. So heat always flows from hotter objects to colder objects. And this makes perfect sense if you think about what hot means. The molecules are moving rapidly, and cold means the molecules are moving slowly. So obviously if these molecules are allowed to touch each other, they will collide, crash into each other. The fast moving molecules will slow down, and the slow moving molecules will speed up from these collisions. So heat will be transferred from one object to the other. So let's talk about the zeroth law of thermodynamics. Suppose the hot object has a temperature of 38 degrees Celsius, and we'll plot this on a temperature versus time graph. You can see a little red tick right there, 38 degrees Celsius. That's the temperature of the hot object. And the cold object, let's say, has a temperature of 4 degrees Celsius. We'll plot that on the graph as well. Now we have a temperature difference, which means heat will flow. Now let's keep track of the temperature of each object as time passes, and let's see what happens. So heat flows from the hot object to the cold object, and as heat flows, the temperatures change. So what we notice in the end is that both objects reach the same temperature, in this case 20 degrees Celsius. We notice that the hot object cools down, the cold object heats up. The reason is because the energy is being released from the hot object. The molecules are losing kinetic energy, whereas the cold object is absorbing this energy. Its molecules are gaining kinetic energy. And this is the zeroth law of thermodynamics. It says that heat flows until the two objects have the same temperature. That any thermodynamic system wants to approach a state of thermal equilibrium. So there's a general tendency for when objects have different temperatures that they will attempt to equalize their temperatures. That these temperatures will reach a state of thermal equilibrium. And this is called the zeroth law of thermodynamics. There's a funny story why it's called the zeroth law. It's because it was realized that this was a more fundamental law than the other two laws that had already been discovered. But rather than renumber the laws that everyone had gotten familiar with, physicists decided to simply call this the zeroth law of thermodynamics. So let's talk about the heat transfer mechanisms. So we know that heat is going to flow from hot objects to cold objects, but what are the ways in which this is accomplished? So the first way is called conduction. And an example of this is when you fry an egg in a pan. The egg and the pan are in direct contact with each other, so internal energy will flow from the pan, which is hot, to the egg, which is cold, and this flow of heat will cook the egg. This is called conduction. Conduction is a transfer of energy due to physical contact. So what this means is that the molecules in the two objects are physically contacting each other. They're physically touching, and energy is transferred due to this contact. So in other words, we can say that conduction is touch. When two objects touch each other, heat is transferred by conduction. The next mechanism is called convection. I'm showing an example of a fire, and the smoke rising up off the fire is because convection is the transfer of energy due to the motions of a fluid. And so what happens is we have the smoke. This is a gas, a fluid, and the smoke is rising up off the fire. This is carrying the heat from the fire up into the air from this fluid motion. This is called convection. So you can think of convection as currents, like wind. So convection is the flow of a fluid. So you're transferring the heat by fluid motion. The final heat transfer mechanism is called radiation. These light bulbs in this picture are radiating light. And that's because radiation is a transfer of energy due to electromagnetic radiation, or electromagnetic waves. This is simply just light. I mean, our eyes can only see visible light. So what's happening here is the light bulbs are heating up, they're getting hot, and they're releasing this light. If you were to put your hands near the light bulb, you would feel this warmth, this heat being released from the light bulb. What you would be feeling is radiation. So in other words, we can say that radiation is simply light. So what I want to do now is go back to each of these heat transfer mechanisms and go into more detail about each and explain the physical process that's occurring that causes heat to transfer. So let's go back to conduction first. So the idea is that when two objects are in direct contact, their actual molecules in the object are colliding with each other. So if you look at this picture, we can see at the bottom we have hot molecules, and at the top we have cold molecules. The hot molecules are moving more quickly than the cold molecules. So what happens is when these molecules collide with each other, when they crash into each other, there's a transfer of energy from the hot molecules that are moving quickly into the cold molecules that are moving slowly. So what happens is the fast moving molecule is going to slow down. It's going to transfer its energy to the slow moving molecule. So the end result is we have energy being transferred from hot to cold. We have heat transfer. Let's take a look back at convection. So the idea in convection is that when a fluid is heated, a gas or a liquid, when it's heated, it becomes less dense, and that will cause it to rise upward. When you heat something, it expands. The air that's next to the heater, that gas is going to be warm, and so it's going to expand and it's going to rise upward. As the warm air rises, it pushes the cold air down. And this creates what's called a convection cycle, because now the cool air, which was forced down by the rising warm air, is then placed next to the heater. It will get hot, and then it in turn will rise upward. And so we create this cycle of heat flow, where the heat flow is actually caused by the molecules themselves flowing and moving through the air by these currents. So this is why the smoke from a fire rises upward, because as that air is heated, it expands and rises up into the sky. This is the reason why explosions create mushroom clouds. It's because of convection. Let's talk about radiation. Any object that has a temperature gives off thermal radiation. But normally thermal radiation is invisible. We can't see it unless the object is very hot. So for example, the sun is 6,000 Kelvin at its surface. This is hot enough that we can actually see the thermal radiation from the sun. So the earth is lit up by the thermal radiation from the sun. This is what keeps us warm. If you go out on a hot day and you feel the warmth from the sun coming down, you're feeling the thermal radiation from the sun. Not only are you feeling it, but you can also see it because the sun is very hot. On the other hand, human body temperature is only 310 Kelvin. This is not hot enough for the thermal radiation to be seen. However, the thermal radiation is still there. If you have a special camera called a thermal imaging camera or an infrared camera, you can actually see the radiation being released from our bodies. And here's an animation of that on the left-hand side. This is a color representation of the temperature of the different places within this picture. Since the thermal radiation is invisible to the human eye, we have a computer that detects the thermal radiation and then transposes it into a color that we can actually see. You can see the scale there for the temperatures. We see that purple and blues are cold, 20 degrees Celsius, room temperature, whereas the hot areas are yellow, red, and white. You'll notice that the glasses are of the colder color. Now why is this? Is this because the glasses are cold? And actually it's not. It's the glasses are room temperature. And what's happening is that they're actually blocking the infrared radiation, this thermal radiation, being given off from the warm skin beneath the eyes. That radiation can't pass through the glasses. This is the reason why you wear clothing. It's because the radiation can't get through your clothing. So it keeps your body from losing heat due to radiation. It prevents heat loss from radiation. So the clothes keep you warm. On the right hand side we have an Indy car and a thermal image of the tires on the car as the car makes turns and moves throughout the course. And you'll notice in certain times there's this bright flash of light. We notice this anytime that there's braking or turning. You have this friction that's rubbing against the tire, making it hot, and so there's more thermal radiation being given off. So remember that any object that has a temperature gives off thermal radiation. The higher the temperature is, the more energetic this radiation is. And if it's hot enough, we can actually see it with our eyes. And this is radiation. So let's look at some examples. So here's a campfire. Within this picture are all three heat transfer mechanisms taking place. Let's start with conduction. Can you find an object in this picture which is heating up because it's touching a hot object? And it's the logs. The logs are in physical contact with the flames of the fire. The logs are heating up by conduction. Can we find a place where there's convection, where there's a flow of molecules, where warm air is rising upward? And in fact, we see it from the smoke from the fire. It's convection. The smoke is rising up off the fire. As the fire heats the smoke becomes less dense, it expands and rises up off the fire. So this warm air from the fire is rising upward, and we can see that from the smoke. Lastly, we're looking for radiation. So radiation is a transfer of energy from light. So we can see the light of the fire. There's this warmth coming off from the fire. We don't want it to be touching the fire, conduction, and we don't want it to be rising above the fire, so we want it to be near the fire, radiation. We want it to be radiating out from the fire. So that would be the rocks. The rocks are getting hot from a distance. So this radiation is going outward from the fire and heating up the rocks, even though the rocks aren't touching the fire and the rocks aren't above the fire. They're still raising temperature by this heat transfer due to radiation from the fire out to the rocks. So looking at this all together, we can see the three heat transfer mechanisms taking place from a fire. We have convection, the warm air rising up. If you put your hands above the fire, you can feel that warm air rising up. Conduction, if you place a hot poker into the fire, the poker will get hot, sometimes even glow if the fire is hot enough. And lastly, we have radiation. When you sit next to a fire and you feel the warmth from the fire, you're feeling radiation. Okay, let's practice. So I'm going to give you a sentence that's describing some sort of energy exchange between two objects, and you're going to tell me if it's conduction, convection, or radiation. Here's the first one. You put your feet in a hot jacuzzi. Your feet are going to warm up. You're going to feel this heat transfer. And what are you feeling? Are you feeling conduction, convection, or radiation? Well, since your feet are physically touching the water, that's conduction. You hold your marshmallow next to a fire to cook. You're not holding the marshmallow above the fire. You're holding it next to the fire. You're not holding the marshmallow in the fire. You're holding it next to the fire. So this means it's radiation. If it was in the fire, it would be conduction. If it was above the fire, it would be convection. This is radiation since it's next to the fire, just like the rocks in the previous example. You touch a hot stove and get burned. Ouch. This is conduction because you're physically touching the hot stove. And lastly, steam rises up from a pot of boiling water. Is that conduction, convection, or radiation? And it's convection. Steam is rising up, warm air rises up, and that's convection. So that's it for PHYZR number 14. Hope you guys have a wonderful day. This has been Mr. Keppel. I'll see you in class.